term fluid does not refer to just liquids like water, but also to gases. And so fluid mechanics is the study of the behavior of fluids, whether they are at rest or in motion. Now, fluids are characterized by a variety of physical properties. Among them, some we have seen before, like density, which is mass per unit of volume, pressure, which is basically stress, which is force per unit of area. So in SI units, that's pascals. In English units, the standard is PSI, or pounds force per square inch. And then a new material property that we're introduced here is viscosity. So viscosity is a measure of a fluid's resistance to flow. So that's measured in Newton seconds per square meter or pound force seconds per square foot, depending on if we're in SI or English units. So the pressure of a fluid is measured either as absolute pressure or as relative to the atmospheric pressure. And so this type of pressure is called the gauge pressure. So basically, a gauge pressure here on Earth at sea level would be 0 pascals. But of course, we're not living in a zero pressure environment. It's just that the gauge is scaled to be at 0 for what's going on at sea level. And so the absolute pressure then is going to be the gauge pressure plus whatever the atmospheric pressure is. And so at sea level in SI units, the absolute pressure is 101.325 kilopascals. So even though our gauge on a bicycle pump or whatever is going to say 0 at that pressure, we know in fact that's the actual pressure that we're experiencing. When fluid is in motion, we characterize its motion by how smooth it is. On the smooth end, we've got laminar flow, meaning when we're at low speed, whether it's a liquid or a gas, the fluid flows in parallel layers which slide past each other. If we think about water through a pipe, there would be this kind of parabolic profile that we see here where it's fastest in the middle, with friction causing there to be 0 flow at the walls. There wouldn't be any whirlpools or eddies or anything like that in a laminar flow. Versus turbulent flow, if we think about like in the ocean, when you've got waves crashing, it's chaotic, the movement of the flow. It's undergoing irregular fluctuations. The speed is changing all over the place. It's pretty much impossible to predict. The Reynolds number is a way that we can quantify the characteristics of a fluid flow and categorize it as either being laminar, in transition from laminar to turbulent, or turbulent, based on its numerical value. The way we calculate the Reynolds number is by taking the density, multiplying it by the fluid speed, and then times the distance, which is really referring to the diameter of the pipe or whatever the fluid is flowing through, and then dividing it by, and the Greek letter mu here, it represents the viscosity discussed earlier. And so again, if we have a number below 2,000 for our Reynolds number, then that's going to be a flow that's going to be laminar, orderly, smooth through the pipe or whatever. In between 2,000 and 4,000 for the Reynolds number, it's going to be in transition from laminar to turbulent, so it'll be mostly orderly, but there will be periods of eddies and whirlpools that pop up from time to time. And then we're going to see that chaotic flow, turbulent flow, when the Reynolds number is larger than 4,000. So here we'll verify that the Reynolds number is indeed dimensionless. So the density in SI units is kilograms per meter cubed, times the fluid speed, which is meters per second, and then times the distance, which we said was the diameter of the pipe, so that's going to be in meters. And then we're dividing by the viscosity. So instead of dividing by this quantity, we're going to go ahead and multiply by the reciprocal. So we're going to have meters squared over newtons times seconds. Now, in order to have all of our units match up so we can show that we can cross cancel everything away, we're going to need to make an adjustment on those newtons. So we've got kilograms over meters cubed still, times the meters per second, times the meters. We've got the meters squared and the seconds, and then those newtons, if we recall, are kilogram meters per second squared. So we've got that newtons in the bottom here, so we now have it as kilogram meters over second squared, but just the reciprocal of that. And so indeed, we have a cross-canceling bonanza. The kilograms go, we've got 1, 2, 3, 4 meters on the top. There's 3 and 4 on the bottom. And then we have a couple seconds on the bottom, cancel out with the second squared on the top. We can also confirm that the Reynolds number is dimensionless in English units. So we've got the density is going to be pound mass per cubic foot. The velocity is the speed is going to be feet per second. Then we've got the distance or the diameter of the pipe, so that's going to be in feet. And then we're going to be dividing by the viscosity, so I'm again going to multiply by the reciprocal, so I'm going to end up with feet squared over pound force times seconds. Now if we look at this, I think it should be obvious that we are definitely not going to have everything divide out in this case, and that's because we have this pound mass and pound force in this expression, which means that G sub C is rearing its ugly head for us again. So we have to divide the Reynolds number by G sub C by 32.2 pound mass times feet over pound force times second squared in order to get the units to work out. So that's something that we have to remember when we're working with the Reynolds number in English units. So for our purposes here, since we're just trying to show that we're going to be dimensionless for the Reynolds number, we're going to divide by the units of G sub C or just multiply by the reciprocal. So I'm going to have pound force and second squared on the top, and then I'm going to have pound mass and feet on the bottom. And so indeed, I've got pound masses that go, pound forces. I've got 1, 2, 3, 4 feet on the top. There's 3 and 4 on the bottom, and also 2 with the seconds. We've got 2 seconds on the bottom, 2 seconds on the top. But we would not see these units all cancel out without dividing everything by G sub C, as is necessary when we've got pound mass as our mass unit in English units. So now we want to find the Reynolds number for water flowing through a pipe under the conditions described here. So for the Reynolds number, we start off with the density. So that here for water is 62.4 pound mass per cubic foot times the velocity. So that's here. So that's 6.75 feet per second times the diameter of the pipe, which is this 3.25 inches. Now hopefully we're recognizing that that is not matching up units wise with the feet that we need, so we are going to have to introduce a conversion factor of 1 foot per 12 inches, and then we're dividing by the viscosity, and so we can see the viscosity number given to us there, 2.35 times 10 to the negative fifth pound force times seconds over feet squared. And then of course we have to make sure to remember we're going to have to divide our answer here by G sub C. So by 32.2 pound mass times feet over pound force times second squared. So it's always a good idea to include your units in your calculations so that we recognize that we've got this mismatch of pound mass and pound force, and we're supposed to end up with a dimensionless quantity for the Reynolds number. So we're only going to catch that if we include those units in our calculation and then recognize that we have to divide our entire answer by G sub C. So in the end, if we push buttons on our calculator, we should end up with an answer of 1.51 times 10 to the fourth. And so if we compare that number against the guidelines for characterizing flow of fluid, we see that's clearly above that 4,000 threshold for turbulent flow.